Welcome, Heartland and Leader friends. I'm so glad you're here. I'm Cindy Zulsdorf. I get to work with the great folks at Heartland and Leader. And if you are planning an IP installation at your station or just wanting to know what to expect someday down the road, this webinar is for you. You're definitely in the right place if you've got that sort of SDI to IP transition on your mind at all. And we're going to get into some of the top questions that Steve and Joe hear about, including how do you get your feet wet with IP? Like, what's a good sort of way to start maybe a sandbox approach? Another question that comes up that they're going to get into is what's a common challenge that, like every engineer hits when they start with ST2110. And we'll talk a bit about sync, of course. How do you integrate PTP and your existing sync system and make everything work together? And so I am going to throw over to Joe at Heartland. Over to you, Joe.
Thanks, Cindy. So for those who don't know me, I'm Joe Turbolski. I'm Director of Sales here at Heartland Video Systems. We're pleased to partner with Leader America on this webinar covering these SMPTE 2110 IP transitions. HVS has been supplying customers in the U.S. with quality communication equipment, professional installation services, and ongoing technical support for over 20 years now. And we've partnered with leading manufacturers like Leader to help bring your solution from concept to on-air reality. During this 60-minute webinar brought to you by Leader and Heartland, Joe Trombetta and Steve Holmes from Leader will discuss the solutions we hear most frequently from our broadcast engineers as they deploy these systems. So I'm going to turn it over to those guys.
All right, thank you, Joe T. So this is the roadmap for this talk. First, we're going to look at the transition challenge, then the sandbox approach. That's how you can get your feet wet with IP. First time ST2110 issues, and that's understanding where Blackburst, tri-level sync, PTP, and BCMA each fit. Some sync coexistence between Blackburst, tri-level sync, and PTP, whether you really want to sync systems, resilience, hybrid integration, the need for combined SDI PTP 2110 measurement. Then we're going to dip into ST 2022-7, the operational lessons that come from testing instead of assumptions. Going to look at reference mismatch, and then you obviously want to avoid that at all costs, and then questions. So this is a humorous way of saying do not begin your IP migration by touching the live core. Start in a controlled environment, learn the timing behavior of your devices, and prove your assumptions before you scale. A lot of first projects struggle because teams buy 2110 capable gear and assume interoperability equals production readiness. In reality, boundary clocks, endpoint behavior, multicast controls, NMOS, and failover behavior all have to be characterized. So the advice is to treat ST2110 adoption as an engineering program, not a feature enablement exercise. So the sandbox approach, SMPTE ST21 Sandbox is an isolated test environment for designing, validating, and troubleshooting media over IP workflows without putting your live services at risk. This includes the 4 foundations to always verify first. So PTP ST2059 timing, multicast behavior, NMOS control and discovery, and ST22, 2022-7 redundancy. So this matters because each of those layers can look healthy in isolation, while the end-to-end chain is still unstable. For example, PTP can lock, multicast can pass, NMOS can connect, yet your packet timing or path diversity can still be wrong. In practice, the sandbox is where you learn vendor behavior, establish your golden configs, and build acceptance tests before equipment reaches the main facility. So let's dive into the sandbox a little bit more. So here's how to make a sandbox more concrete. At a minimum, you need a PTP Grandmaster, a boundary clock capable switch, then preferably PTP by GPS, some SDI source material with a gateway conversion, a measurement instrument that can observe PTP, SDI, and 2110 simultaneously, and a basic NMOS system. You do not need lock indicators. You need timing comparisons, packet jitter analysis, path delay logging, and trend capture over minutes to days, because many faults only show up as drift, intermittence, or failure anomalies over time. So where does Blackburst and tri-level sync, PTP, and the BMCA all fit in? So Blackburst and tri-level sync remain important on the SDI side, while PTP becomes the timing basis for ST2110. PTP is not a pulse reference, it's a time-based system derived from epoch, and BMCA is the mechanism that determines takeover between the timing leaders. This matters because many facilities think in terms of genlock pulses, but IP timing requires thinking in terms of time distribution, announce messages, clock quality, and endpoint behavior during leader changes. So now let's look at the transition challenge. This example shows the SDI side requiring Blackburst and tri-level sync, and the IP side requiring PTP, then asks how to keep both in sync under all conditions. The specific warning here is that if you derive PTP from Blackburst, you're referencing a sub-microsecond PTP system to a less precise timing source, and if black is lost, the two timing domains can diverge. This can work until it doesn't, and when it doesn't, the failure mode may be subtle before it becomes visible on air. The issue is not only nominal lock, it's what happens during reference loss, holdover, and restoration. So this is the inverse model. We use a high-quality PTP source, potentially a cesium-backed system, and locking the SDI SPG to PTP. That improves timing alignment between the SDI and IP domains, but if the PTP reference is lost, you can still end up with split sync behavior between the two sides. So the main lesson is picking one domain to feed to the other does not remove the design problem. It only changes which failure mode that you have to engineer around. That's why it's recommended to design common source synchronization and a specified failover. So, sync wars. This is a consequence in operations. If your sync systems disagree, you do not get just untidy engineering, you get service interruptions, frame slips, packet timing faults, and potentially an off-air event. It's also a reminder that redundancy without ensuring synchronization can create more complex fail modes, not fewer. So this is the preferred strategy. We derive SDI, Blackburst tri-level sync, AES, EBU, LTC, NTP, and PTP from the same oscillator inside the sync pulse generator, with the system locked to GPS or GNSS. That way, if GPS is lost, everything falls back together onto the same internal oscillator and stays in sync. It's equally important that when GNSS returns, slow lock prevents a disruptive regen lock event. That's the kind of detail that matters in real facilities because recovery behavior can be as dangerous as the initial fault. So the way to think of this is one timing heart, many outputs, shared holdover, and controlled recovery. So here we're looking at an air-gapped 2022-7 style thinking and why PTP can get awkward in hybrid systems. The main issues are that endpoints are not necessarily mandated to use the BCMCA the same way. Some can lock to a biased port, some average, some dislike GMID changes, and split brain timing between red and blue can become a real risk. This is a strong warning that endpoint behavior matters as much as your switch architecture, If endpoint clock selection is inconsistent, your elegant timing may still behave unpredictably in production. So here we're going to have some red markers. So isolating each path doesn't guarantee the timing sanity. The network can be architecturally clean while the endpoint clock decisions still undermine the resilience of the system. So in this diagram, A and B are not primary and backup in the classic sense. The packet picker selects the first valid packet to arrive. That gives clean switching and RTP sequence behavior, tolerates complete failure of one path, and costs roughly double the network bandwidth. Normal operations should show packet selection distributed across both paths, not everything preferring one side forever. So as you can see here, we walk from the left, the sender, through a network failure, errored packets going into the receiver, and the packet picker selects those that are good. So now we're going to look at reference mismatch. So the core mismatch problem is primary and backup SPGs can both output blackburst and tri-level sync and PTP into a paired 2110 network. But if their analog and PTP phases are not aligned, redundancy at the device level does not equal reference integrity at the plant level. The danger is thinking that primary and backup are enough, while the actual issue is whether or not both remain phase coherent through a failover event. So you're not just protecting the packet flows, you're protecting cross-domain timing relationships. So here's a real-world example of a mismatch. The two grandmasters differ by 0.940 microseconds. This is due to a phase difference. In this case, it was a lack of antenna cable compensation. So a sub-microsecond number can look harmless until you remember it's large relative to a tightly engineered reference environment. It's important not to just verify lock state, but also to verify phase alignment, cable compensation, and trend the offset over time. So this shows a PTP-only link between spines, every spine connected to every leaf, scaling by adding leaves for node count and spines for bandwidth, and using a boundary clock leaves to reduce message load on the grandmaster. So this is the preferred variant, adding a dedicated PTP-only distribution switch between the primary and backup grandmasters and the spine layer. So separating timing distribution from media transport, where appropriate, can simplify behavior and reduce troubleshooting question marks. And with that, I will hand it over to Steve.
Thanks, Joe. Yeah, as you look through those last two slides, the important thing there is by having those links, the two SPGs have to talk to each other for the BMCA to actually work and for you to have proper failover. A lot of people test their systems by just walking up and yank the PTP output out of one of the generators. And then, yes, you will fail over to the second generator, but that doesn't look at all scenarios, like looking at what happens if you just lose GPS or GPS gets jammed or something happens. So what actually happens here is when both generators fire up, they go into listen mode and they're listening to the announce messages. And the announce messages are automatically sent from both generators. And it will tell you what domain they're on, what priority 1 is, what the clock class is, what priority 2 is. And then the BMCA will take over and say, based on the criteria that I'm seeing between these two generators, I'm going to pick the generator that will be the grandmaster. So it is all based on looking at the priority 1 message, the clock class, and the priority 2. And if you look here, priority 2 is a value of 1. And on the second generator, the priority 2 is a value of 2. And the lowest number wins. So in this case, the unit on the right became the actual grandmaster itself. And going through this, if we were to have a fault, your GPS got hit by lightning, something happened to the cable run or something, and you actually lost your GPS antenna, the SPG would go into what is known as holdover mode, which means that it's now running on its internal oscillator, which is phase locked to everything, but it's going to go into what we call clock class 7, which is no longer GPS locked, but I am currently the correct phase and correct frequency, but the grandmaster on the left is still GPS locked. So it still shows a clock class 6. And since clock class sits above the priorities here, the second generator will automatically become the grandmaster, tell the second generator on the right, in this case, to go passive because he is a better clock source than the one on the right. Now, the beautiful thing about this, in this case, this is all done kind of under the hood with the two units talking to each other. Then all of a sudden, one generator just goes passive, the other generator comes online, and all the receivers are still getting PTP perfectly. And everything happens just fine. And if the network corrects itself, you have the choice for it to auto recovery or not auto recovery. And I'll talk a little bit about that some of the next few slides. But if you don't have priority 1 set correctly under this same scenario here, if you look, I have priority 1 of 1 here on the right, but I have priority 1 of 2 on the left. The second unit will never become the grandmaster until PTP is 100% missing. So a antenna fault or a GPS fault or a PTP fault of some source that changes its clock class or its quality, the second generator will never walk in because of priority 1 being a value of 2 on the left-hand side over here. That takes him out of the BCMA voting pool. And this generator with a clock class of 7 on the right-hand side is going to remain being the grandmaster. So it's really important to understand the priorities, the clock class, and how to set up a proper network and how to test that network. You do need to test not only just removing PTP, but you also need to test by removing just the GPS lock and have it go into clock class 7 and make sure you do have that change of state all the way through your system. So one of the other things that is vitally important in looking at in a real world scenario is PTP timing. So you can have the system be PTP timed, but what about your SDI network? Your SDI network and your PTP network need to be timed to the same exact timing source and the same exact starting point, because at some point you're going to want to switch between your IP network, your 2110 network, and your SDI network. And you need to be able to switch between those two sources and have everything perfectly synced without going through a complete reclocker. There's no need for it. So the starting point of black is line 0, pixel 0, right here at the top, up here, my 0 by 0. Well, PTP should be at the same exact point that black burst is. So when you look at your IP input and you look at timing, and you're referenced against black, it should come up with 0 by 0. Now, your horizontal offset is never going to be absolutely 0, and your horizontal offset is going to walk just a little bit. And the reason it's going to walk just a little bit is we're dealing with packets and switches. And a switch is a statistical multiplexer. And what it's going to do is at some point, a packet's going to show up. When multiple packets show up at the door and need to get out, the switch is going to statistically say, hey, this packet goes out first, you go right behind him. And at some point, PTP may go out first, or video may go out first. And packets get in front of other packets, and packets get behind other packets. So there's always just a little wobble in what's happening. What we're really worried about is the data that's inside of that to actually remove that little bit of wobble. But your horizontal offset, you are going to see just a little bit of movement in it. The thing that we're really interested in is, where does my 2110 video actually start? Because since in 2110 we don't send the vertical or horizontal intervals, we just send the active live video shown here in green. If you're a 1080i system, you know that your vertical interval is 21 lines. So my video for my 2110 system should start 21 lines later. And if you notice here in this particular instance, and this is real off of the live system here, it was 20 lines out, not 21 lines out. And I have not seen a standard that says it has to be this or has to be that. What I have seen from just real world working on this for almost 15 years is looking at the timing and what systems will withstand. And it's basically plus or minus about 2 lines. So if you're within about 2 lines here on the offset, you'll be absolutely fine, because the data will tell it exactly where to start. The other thing we need to make sure is that when we have a red-blue network or an amber-blue or AB, whatever you want to call the 2 links, that the timing between the one link and the other link are identical to each other, since they're being fed from the same SPG at the very top of the stack and being spread out to both sides of the switch, that everything follows suit all the way through, and your timing on both sides of your network are correct. And then the last piece of timing we really want to look at is the PTP against FPT, which is first packet time. And essentially what that really means is the first packet that we are going to decode to actually make video. And this is the most important timing model that we need to verify. And again, it should be the width of that vertical interval, either 21 lines out or 42 lines out. And the other thing is, if you are running UHD, either 6G or 12G, it actually has the same timing model as 1080p does. It would be 42 lines out also. So these are 3 measurements that you need to make when you put your system up, but you also need to spot check these measurements at different times going through your system, just to make sure the health of your network is working correct. And as Joe pointed out earlier, we have a grandmaster on top. In this case, we have our ECO in the middle for the black and baseband signals and SDI test patterns. The SPG on the bottom is in what we call passive state. It's listening, but it's not outputting PTP. It has all of the SDI and reference signals all going into the ECO here. And the ECO is outputting the primary unit to the SDI network on the right over here. And the top SPG is providing the PTP to all of the network. There is a interconnect cable that we have made to take care of mismatches. And what we mean by mismatches is that we can now sync and have a cable that interconnects the ECO to both generators so that we can keep failovers together. And what I mean by that is we can get into states where you could have a PTP failover, but your baseband signals won't fail over, and you can end up working off of two different SPGs. In this scenario right here, we're looking at the same setup, and everything is working off of our grandmaster, our primary unit. But if I have a failure here of my GPS on my top SPG, it is going to go into holdover mode, clock class 7. The second generator on the bottom down here is going to become the grandmaster, but my baseband signals are still absolutely fine. So the ECO isn't going to do anything. So all of my baseband signals are still running off of the top generator. My PTP is coming off of the bottom SPG. This generates two issues. One, slight timing issues, since the top unit is no longer completely locked. The bottom unit is locked. There is a slight phase difference that will occur between the two. The second thing is a maintenance nightmare. When your engineer goes in to work on this and he knows that the PTP has switched over, he isn't really thinking about the SDI baseband signals. And quite often they'll go in and grab that top generator and take it out of service, which is now going to cause a hard fault to all your baseband signals, and everything is going to take a hit when he tears that generator down, and the ECO then finally switches over to the other grandmaster. And what you end up doing is you having this scenario where you've got part of your system running on two different sync generators, which is a maintenance nightmare as well as just a timing nightmare. What we would like is to set up so that we cause a condition that will make the ECO switch, but do an electronic switch so the baseband signals don't see it, so that we force the baseband signals and force the ECO to switch so that everything now becomes working off of the grandmaster, what is the PTP grandmaster. That completely leaves the top SPG wide open for the engineer to go do maintenance on that generator, fix the PTP issue, whatever it may have been, and then turn around and bring the system back to normal when everything is completed. The same thing can occur that if either the output of your baseband test signals, your black burst to tri-level sync goes bad, the ECO is going to switch to the backup ECO, and I've got the same condition, but this time it's from the blackburst side. We want to be able to force the grandmaster to walk down and do a soft walk to the second grandmaster down on the bottom that is in passive state, and make it the grandmaster, which is just a soft walk within the network, just saying, hey, I am now going to take over. We're going to change your status so that you are not better than I am. And the second generator will take over. And again, that top unit, in this case for the fault, is completely void of anything that is running your system. The second thing that we can do is set PTP so that it doesn't auto recover. So PTP was not invented for the 2110 world. PTP has been around for many, many, many years, long before we decided to use it for video data in a 2110 environment. And in the data world, the telco world, they use it and it's auto recovery. So if something happens, it switches over to the grandmaster switch. And if the signal comes back, it auto recovers and walks right back. We don't like that in the video industry. We like to be in control, just like we do with the ECO in the SDI world. It switches. Even if you fix this fault, it's still going to stay switched until the engineer has tested it, walks up and says, switch back. We have the same condition that we can apply to the PTP signal on the second grandmaster and say, even though the primary grandmaster on top up here has fixed itself, do not switch back until I tell you to turn around and switch back. That way the engineer has full control and can 100% test the top SPG that the black signals are all working correctly and that the PTP and GNSS are 100% done. And I can hit a changeover reset and I can hit a priority 1 reset. And the priority 1 reset will turn around and switch the PTP back, and that way the engineer is always in 100% control of what happens within the network. So it's really, really important to have that link between your grandmaster and the ECO and the second SPG, so that you as the engineer can always control the failure scenario and how things come back and how we go out within our network here. So I want to thank you for going through this. This session went a little quicker than the 100% allotted time, but we just wanted to get these points out to you that are very, very top of mind when you are introducing 2110 and introducing PTP to your network. That is honestly is best not to have 2 SPGs because they can always get separated. You want to migrate your system to a single SPG that always has all the signals coming out of it. That way, if it does something happen and you lose all GPS, even to both generators, everything that's on the generator, if it starts to sink and just start drifting, every single thing in the house is actually drifting together and nobody will ever see it. If the system comes back, it turns around and will turn around and slowly sink forward or backwards to what's going on. So we want to thank you very much. And Joe from Heartland, any last words?
Well, it's very interesting to see all the complexities that go into the SPGs and the timing, especially when we're talking about these hybrid systems. So I really appreciate the expertise of Joe T from Leader and Steve Holmes. Very interesting, very thorough overview, and we appreciate everybody that's attended.
Cindy, we've got time for a question or so.
So, Steve, you were talking about PTP infrastructure, and one of the attendees is asking if you could talk about NTP versus PTP. Thoughts on that?
Yes. So black burst is a 1 microsecond, roughly a 1 microsecond timing reference. NTP is about a 1 millisecond timing reference. It's also a polled, the receiver has to go grab it and ask for that. There is some protocols within it to try to remove the network delay, but it can never remove all the network delay. So NTP is about number 3 or 4 on the list as far as lock quality.
Got you. And another question around PTP. Somebody was asking, what does it mean if a PTP generator is passive?
What passive means is that it's listening to all the announce messages go back and forth, but it is not currently outputting PTP. So it's just sitting there waiting to come online when the BMCA says that its clock quality and priority 2 are better than the generator that is online. So that's what passive means. It's just sitting there. It's ready to go. It's listening to the announce messages. It's sending its announce messages to the network. And it's just waiting to go online as soon as it becomes better than the generator that's online. So if the primary SPG, the Grandmaster, goes to clock class 7, and that unit is still clock class 6, he's going to go from passive to active and tell the second generator to go passive.
Now, we've got somebody here that talked about having to do a changeover test on air and shared a little bit about how it went for them. But have you run into that where people had to do a changeover test on air? What are your thoughts?
I would do it at about 3 o'clock in the morning, to tell you the truth. It's just because you don't know multiple things. Yes, you want to build it, but yes, you do have to test it. You do have to test it with live traffic and on the air and make sure everything does work. But there is so many little things that could happen. You want to do it off prime hours, definitely, and go through all of it, because either if it's a required maintenance activity after X number of years, or just bringing the new system online, you've honestly got about a 50-50 chance that it's going to work perfect the first time. With
And when
PTP
it doesn't
plus
work,
black and everything else.
when it doesn't work, what is the result? What are some results one could expect?
Well, remember that little slide that says, please stand by? That's typically what happens. it takes you off air the majority of the time. So it is devastating. And, it's, yeah.
Now, I feel like you talked about a way to protect against that. And I know that Heartland helps with this piece of it too. But if I can go back to the sandbox discussion you had earlier, somebody has asked, what elements do I need to do that IP sandbox that you showed earlier? What's a good way to start? What do you think?
Well, like we kind of showed in that picture, and we will be posting all these slides to both the Leader YouTube site as well as the Heartland YouTube sites. And we will send you emails so you will have links to them. And we will make this available shortly after. Give us a little time to dress it up and get it out there. But yeah, so in doing that, this will help you get to a point that hopefully when you do build this into your system, those issues will either be very minor or will go away altogether. But yeah, you need a PTP Grandmaster. You need a switch that's hopefully a boundary clock switch. The source of video through a gateway, and the reason I showed a gateway in when I put that slide together is you want to be able to compare your SDI against the IP that's coming through the network. And when you're doing captions, you're doing triggers, you're doing VChip, is all of that data surviving since it is on its own multicast? And do all those points actually come through the system? And then also you have the ability to do all those failure scenarios and see where you may have forgot something that wasn't set right and be able to, help go through everything.
That's perfect. I'm going to bring all five of us on screen for everybody to see here. So we've got Tom, Joe, and Steve. Thank you all for being here for this webinar today. And I love, Steve, that you wrapped up with how somebody could put a sandbox together. And I know, Joe Turbolski, that's exactly your wheelhouse, that you can help people put that together for their stations. Any final words from any of you?
Just want to say thanks for everybody that attended. We appreciate your time. We know it's valuable. We'll be doing some more of these later this year as well, so stay tuned.
Yeah. And with Heartland and Leader together, we've got everything that you need to be able to put your system together and have it trustworthy and reliable. And we have the information here on both sides of the house to be able to have you send us an email. We will answer the emails and help you get through any issues you have in building up your sandbox.
All right. Thank you all. Have a beautiful day.
Thank you very much.
Thank you.
Take care, everybody.
Okay.